and to Janu for her fantastic lecture. So now the time for Professor Ali Övgün. May I request Professor Ali Övgün to present his lecture?
Hi to everyone. Okay, let me share my screen.
Yeah, Charu, please stop sharing.
Yeah, if you want.
Then only Professor Ali can get in. Yeah, you can click there. Yeah.
Okay. Can you see?
Yes.
Okay. Hi to everyone and welcome to my presentation today. So I will talk about the testing modified gravity theories using the weak deflection angle and the black hole's shadow. I am Ali Övgün from Eastern Mediterranean University, North Cyprus. And here you can see some references related to my works, which we publish with my collaborators in different journals. And a black hole is a region of a spacetime where gravity is so strong that nothing, nor particle or even light, can not escape from it. But they are very simple object. You can define the black holes with only using the event horizon. And at the center of the black hole, there is a gravitational singularity. This region is where the space-time curvature become infinite. As you can see now, the black hole, the simple object with horizon and singularity. And can gravity bend the light? Yes, the light travels through space-time, which can warp and curve. So the light should dip and curve in the presence of the massive objects. So when taken to the extreme, gravity can create some intriguing visual effect that Hubble is well suited to observing also. And we know that the Einstein's general theory of relativity describe how mass conservation distorts the space around them. So, and this gravitational lensing is one of the good tools to observe the compact objects. And another important property of the black hole is that the light rays near the central black hole are expected to be affected by the luminous acceleration disk or other dust that surround the black holes. This acceleration disk is the hot, thin rotating disk formed by matter slowly spiraling toward the black holes. And there is also the photon ring around the black hole, a ring of light composed of multiple distorted images of the disk, and the light making up this image has orbited the black hole 2, 3, or even more times before escaping to us, and it makes a circling, and they become thinner and fainter closer to the black hole. And then what happens? There is a black hole shadow area, and this area are roughly twice the size of the event horizon, and this is also the black hole's point of no return, and that is formed by its gravitational lensing and capture of the light. The matter causes a spreading such that the black hole silhouette shadow is not sharply delimited. So in order to generate a more realistic images of the black hole shadow, the visual appearance of accretion disks or jets is studied with the help of the sophisticated numerical ray tracing programs by several authors in the literature like Bardeen and Luminet, so on. So if you look at the shadow, on the theoretical side, the shadow is defined as the region of the observer's sky that is left dark if there are light sources distributed everywhere, but not in the observer and the black hole. So, and it produces a shadow image. But the important thing is the shadow is not a Euclidean image of the region inside the event horizon, and also it is not the Euclidean image of the region inside the photon sphere. The shadow image is the image of the region inside the photon sphere and increased by the bending of the light rays, and it is approximately is equal to 2 times of the Schwarzschild radius. So what the Event Horizon Telescope image show us? The Event Horizon Telescope is a large telescope array and consisting of a global network of radio telescopes. So recently the Event Horizon Telescope collaboration published the first image of the black hole in the nearby radio galaxy M87. So each antenna split out over vast distances and has an extremely precise atomic clock, and analog signals collected by the antenna are converted to the digital signals and stored on the hard drives together with the time signals provided by the atomic clock. These hard drives are then shipped to the central location, signalized, and then it gives us some images. Because that the gravity bends light from the disk around the black hole, giving it the appearance of a halo, regardless of the angle it is viewed from. And you can see one side is brightest and the other side is dark, because the radiation from the gas and dust moving toward us appear brighter, but on the other side, the radiation from particle moving away appears dimmer. So this imbalance makes the ring appear brighter on one side. And here you can see the photon sphere and also the black hole shadow radius. And another important tool is, this is only introduction, I am going fast for it. Let's look at the gravitational lensing using Gauss-Bonnet theorem. So gravitational lensing is a powerful tool that directly probes all clustering component in the universe through their gravitational effects on light from background sources. So firstly, the gravitational lensing proposed by Soltner in context of the Newtonian theory, and he found the deflection angle with the Cavendish 2gm over rc square. Then Freundlich effort to measure this during an after that Einstein predicted that geometric theory of gravity will exhibit light deflection, and then Freundlich effort to measure this during an eclipse in the Krim in the wartime, and then he is arrested by the Russians. After that, Einstein published general theory of relativity and showed that the new value should be 2 times than the Newton's one. So it doubled the Newtonian value. And then Arthur, using data taken during a solar eclipse in 1919, Eddington measured a value close that of the GR prediction, and then Einstein became famous. So if let's look at the now Gauss, how can you calculate the deflection angle using the Gauss-Bonnet theorem? Firstly, Gibbons and Werner present another approach to gravitational lensing theory, which emphasizes global properties. So specifically, they consider the astrophysically relevant weak deflection not in the impulse approximation, but treat light rays as spatial geodesic of the optical metric, and then use the Gauss-Bonnet theorem. So it turns out that the focusing of light rays is, from this point of view, essential as a topological effect. And hence they find that rather surprisingly that the deflection angle can be easily calculated by integration the Gaussian curvature of the optical metric, but outward from the light ray. And in contrast to the usual disruption in terms of the mass enclosed within the impact parameter of the light ray. So here you can see simply the Schwarzschild spacetime. So you can calculate the optical geometry, which is the two-dimensional geometry, by taking the equilateral plane. And after that, when you calculate the Gaussian curvature is negative. So it means that the geodesics must locally diverge. Then how can two light rays from light source refocus at observer so that the two images of the Schwarzschild lens obtained? So to solving this problem, he used a global theorem to connect the manifolds. So they use Gauss-Bonnet theorem. So Gauss-Bonnet theorem is an important statement about surfaces in differential geometry and connecting the different geometries to their topology. So, and it connects the intrinsic differential geometry of a surface with its topology. And this will be the main tool in exposure. And then they show that it is easy to calculate the asymptotic deflecting angle using this, and it reduced to this simple form. Okay, only you calculate the Gaussian curvature of the optical metric and take the integral, the infinite region of the surface bounded by the light ray, and you can calculate it in the zeroth order approximation. And the topological contribution is therefore here essential to the focusing, and it is in the sense that the gravitational lensing can be understood as a topological effect.
Professor Ali,
Yes,
please
yes.
be quick. Professor Ali, please be quick. We are running out of time.
Okay, and here you can easily calculate the alpha deflection angle for Schwarzschild black hole for m over b. And by using this method, I calculate the deflection angle for the wormhole, and here I show the effect of the lambda parameter on the deflection angle. So it is clear that here the deflection angle is increasing by the parameter lambda. Yes, here you can see the deflection angle is increasing. So after that, I also work on the shadow of the black holes, which is first studied by Singh and then Barden for the curved spacetime, and then it is work. There are different examples in the literature. So for black hole, photon coming from the black hole, by predicting how this photon act around the certain type of the black holes and black hole mimickers. So it is possible to compare the calculated photon path within a picture of black hole. So we can predict how photon acts around the black hole by calculating the null geodesics. So you can calculate the null geodesic. Also, you can use the conservation of the energy and conservation of the momentum. You can derive the null geodesics. And then if you look at the effective potential, you can taking a look at the minima and maxima of the effective potential function of the system. And minima in the effective potential function correspond to stable circular orbit, but maxima on the other hand correspond to unstable circular orbit. And the impact parameter is the perpendicular distance from photon that enter the system to the center of the system. And you can calculate radius of the photon sphere. And using the radius of the photon sphere, you can calculate the shadow radius. For the Schwarzschild event horizon is only 2m, but the photon sphere is 3m, but the shadow radius is 3√3m. And photon entering a black hole system for different impact parameters, as you see in the figure, and the photon with a critical impact parameter ends in a circular motion around the black hole. So this critical impact parameter is very important to find the shadow. The black disk marks the event horizon of the black hole, and for an impact parameter that is smaller than the critical impact parameter, the photon will always end up inside the black hole. And for an impact parameter that is bigger than the critical impact parameter, the photon will end up at infinite distance from the black hole. As you can see the other calculation. And the left side show the prograde circular photon orbit, but the right side show the retrograde circular photon orbit. For the rotating black holes, there's a deformation in the circle, and you can use this oblateness of the shadow to gain some information about the black hole. So this deformation depends on the viewing angle of the observer. So if for the equilateral observer the deformation is strongest, while for the polar observer this deformation is absent. So after that we study by using this shadow calculations, we apply it to the Kerr-Newman-Cassius spacetime with my collaborators, and we look at the effect of the dione on the shadow. What is the dione? Dionic. This is very important thing. Dione is a electric and magnetic charge are together in the spacetime. For example, if you look at this K&K spacetime, you will see that there is additionally a magnetic charge. So the electric and magnetic charge are together. So we calculate their effects on the deflection angle, and you can see that the magnetic charge also decreasing the deflection angle. And after that we generalize it and we calculated the shadow of the this K&K black hole, and we see the effect of the A. When the rotation parameter is increased, the deformation is also increasing. This is expected, but also we look at the effect of the magnetic charge. When the magnetic charge is increasing, here you can see that the it is linearly, the radius of the shadow is linearly decreased with this extra magnetic charge if you compare with the Kerr-Newman black hole. And after that, lastly, this is recently we published a paper testing the generalized Einstein-Cartan-Kibble schema gravity using weak deflection angle and shadow of the cast. This theory is also very important because there is a torsion and there is a black hole solution in this theory. So we simply, I'm going fast, calculate the deflection angle and see this ECKC parameter gamma, that gamma is increased with the deflection angle. So when gamma is increased, what happens? The deflection angle is also increasing. So you can see in the figure. And after that, we also calculate the deflection angle in the presence of for a homogeneous plasma, because in the homogenic plasma there are some chromatic gravitational deflection effects. And when you calculate it for this black hole, you will see that same effect arise, because the omega is the photon, omega E is the electron plasma frequency, but on the other hand, the omega infinity is the photon frequency measured by an observer at infinity. So here the deflection angle depends on the frequency of the photon, and it shows the chromatic gravitational deflections, and deflection angle is increasing in the plasma. And after that, by using the Assoc method, we convert it to the rotating generalized black hole. So when we make it a rotating black hole, we calculate the shadow of this black hole. So let's go to the conclusion. And here, and we see the effect of the gamma on the shadow of the rotating generalized ECKC black hole. The region in angular momentum space is occupied by the Planck orbit for particle in parabolic orbit or photons, so incident upon a black hole from the infinity. Left and right side of the figure show the prograde and a retrograde circular photon orbit. And it is worth noting that since the rotation black hole under consideration is a generalization of the Kerr-Newman black hole, once the rotation appear, this black hole reduced to the also the Rydell-Norton black hole for the gamma is equal 1, and when it will be Schwarzschild when Q is 0. And here you can see that it turns out that the shadow of this black hole is a zone covered by a deformed circle. And as a conclusion, and here when gamma is increasing, what happens? The radius of the shadow is decreasing. And as a conclusion, for both cases, for static and stationary, we have shown that this ECKC parameter gamma plays an important role on the path of photon moving in this curved space-time of this black hole. And in particular, it's seen that the weak deflection is increased with the increase of this parameter gamma. And another remarkable point is that when you remove the plasma effect, you find all the plasma effect when this is going to the zero, the plasma effect on the deflection angle is vanished. And finally, our finding have the potential to indirectly indicate the presence of the torsion that may be source of the dark energy, a mysterious type of energy that permeates all of the cosmos and increase the universe rate of the expansion. Therefore, due to the impact on the gravitational lensing, indirect proof of the torsion also will provide a sound foundation for the scenario in which each black hole is interior in a new universe. So the last question is it possible to get the parameter of a black hole back from the shape of the shadow? So thank you very much.
Thank you. Thank you, Professor Ali. Any
Thank you very
question or query? Any question or query on the presentation regarding the theme? Okay. If there is no question, let us